Good morning, students. Our today's topic is complete norm-linear spaces. So first definition is, what is Banach space? A complete normed linear space is called Banach space. Complete means if you take a Cauchy sequence in that space, then that Cauchy sequence is convergent in same norm linear space. Then we say that the space is Banach space. Now we'll discuss its examples. The first example of Banach space is Euclidean space. Euclidean space means n-dimensional space of real numbers. We will prove that this space is complete normed linear space. Yesterday we discussed that this Euclidean space is normed linear space. Now it remains to prove that it is complete. Now to prove this is complete, we will take an arbitrary Cauchy sequence in this space, and we prove that that Cauchy sequence converges in the same space. So let us take a Cauchy sequence we have denoted by xm. So let xm be a Cauchy sequence in this space. Here each xm, because they belongs to Rn, so each xm will be n tuple of real numbers. Means we can write each element of this space as, if we take element xm from this space that is having n coordinates, first coordinate is exile 1m, second exile 2m, and so on, exile nm. So this is n tuple of real numbers, and this is an element of the Euclidean space Rn. Here exile 1m means the first coordinate of this element xm, exile 2m means second coordinate of xm, exile nm means nth coordinate of xm. Now because this sequence is a Cauchy sequence in Rn, so we can apply the definition of Cauchy sequence. So by definition of Cauchy sequence, for epsilon greater than 0 given there exists a positive integer. Let us take that positive integer is m0, such that for all m and l greater than or equal to existing integer, the norm of xm minus xl is less than epsilon. Here xm is having the n coordinates, exile 1m, exile 2m, and so on, exile nm. In the same way, the element xl we have denoted by exile il, where I varies from 1 to n. Now xm minus xl norm is less than epsilon. By using the definition of norm which we defined in this space, using that definition and finding the value of xm minus xl and putting here, we get summation exile im minus exile il mod square their sum whole raised to the power 1 by 2. That quantity will be less than epsilon. Now because this quantity is less than epsilon, so if we square both sides of this inequality, we get summation mod square of exile im minus exile il is less than epsilon square for all m and l greater than or equal to existing integer. Now because these are non-negative quantities and their sum is less than epsilon square, so each of these quantities that will be less than epsilon square. So from here we get mod, the square of mod of exile im minus exile il, that is less than epsilon square for all l and m greater than or equal to existing integer. So from here we have obtained the mod of exile im minus exile il is less than epsilon for all m and l greater than or equal to the integer m0. And because this is true for every I, where I is varying from 1 to n, so we can say that exile im is a Cauchy sequence of real numbers for each I. For I is equal to 1, for I is equal to 2, and so on, for I is equal to n. We have this as Cauchy sequence of real numbers. But as we already know, the set of real numbers, that is a complete metric space. So that is complete. It means if we take a Cauchy sequence in R, then that Cauchy sequence will be convergent. So here these Cauchy sequences, they will be convergent. So let us take, they converges to exile I. So for every I we have a limit, exile 1, exile 2, exile 3, and so on, exile n. So by using these n limits, we can define the element x having the coordinates exile 1, exile 2, exile 3 up to exile n. And obviously because it is having n coordinates, this will belong to the Euclidean space Rn. Now we have to prove that our Cauchy sequence xm converges to this element x. So in order to prove that, let us take m fixed and L approaching to infinity in the equation second. So if we take L approaching to infinity in the equation second becomes this. And because we already discussed, this sequence is having the limit exile I. So this will become mod of exile im minus exile I, that is less than epsilon for all m greater than or equal to m0. And this is true for every I which is varying from 1 to n. So from here we can say that the mod of exile im minus exile I, that is less than epsilon for every I, and for every m greater than equal to m0. Because these are less than epsilon and because this is true for every I, so there is sum that will also be, so we can say summation exile im minus exile I mod square sum under root, this is less than epsilon for every m greater than equal to m0. And by definition, this is the norm of xm minus x. So we have proved that the norm of xm minus x is less than epsilon for all m greater than equal to m0. So this proves that the Cauchy sequence xm converges to x, and also because x belongs to Rn. Thus we have proved that every Cauchy sequence in this space converges to an element which belongs to the same space. And this proves that the Euclidean space is complete. And because it is also a normed linear space, so this is complete normed linear space. So we can say that Euclidean space is a Banach space. Our next example is, we will prove that the sequence space L infinity. L infinity, this is the space of all the bounded sequences of complex numbers. This is called sequence space. We will prove that this sequence space, that is a Banach space. So in this space we define the norm of an element. If we take an element x belonging to the space L infinity, then its norm is defined by the supremum of mod of xn, where x is the infinite sequence having the coordinates xn. Under this norm, we will prove that this space, that is complete normed linear space. So firstly, let us prove this is a vector space. In order to prove this is vector space, we have to define two operations, vector addition and scalar multiplication in this space. Let us take two elements x and y in the space L infinity. Here we have used the symbol m for the same space. So we have taken two bounded sequences xn and yn of complex numbers. Now let us define x plus y. So because x is the sequence xn and y is the sequence yn, so we can define x plus y in this way. Now because both sequences are bounded and sum of two bounded sequences is again bounded, so x plus y will also be bounded. As we can see, the sequence xn is bounded, so by definition of bounded sequence, xn mod will be less than or equal to k, where k is greater than or equal to 0. In the same way, sequence yn is bounded, so yn mod is less than or equal to some non-negative integer k dash. So xn plus yn mod by triangle inequality, this will be less than or equal to xn mod plus yn mod. This is less than or equal to k, this is less than or equal to k dash. So from here we have obtained the sequence x plus y that is bounded. So x plus y being a bounded sequence belongs to the sequence space L infinity. Now we define scalar multiplication in this sequence space. So let us take a scalar alpha and let us define alpha into x. Now alpha into x, now x is a sequence xn, so this will become the sequence alpha xn. Now because xn is bounded, so we can say that alpha x is also bounded. So we can say that under these two operations, the sequence space L infinity becomes a linear space. Now next we prove that this sequence space is normed linear space. In order to prove this is normed linear space, let us define norm in this space. So let us take an element x belonging to this space. X belongs to L infinity, so x will be a bounded sequence, and that sequence we have taken xn. Now we define norm of x is equal to the supremum of mod of xn. Now because x belongs to the sequence space L infinity, so x is bounded. Because x is bounded, so we can say that this supremum exists, and obviously this is a non-negative quantity. Now because this is non-negative, so first condition for this function to be a norm is satisfied. Next condition, if norm is 0. Now norm is 0 if and only if this quantity is 0. Now this quantity is 0 if and only if xn mod is 0. Mod is 0 if and only if element itself is 0. Now because n varies from 1, 2, 3 and so on, so it means we can say that x1, x2, x3 and so on, all the coordinates of x will be 0. So we have x is equal to 0. So this proves the second condition, means norm of x is equal to 0 if and only if x is equal to 0. Now next condition, absolute homogeneous property. For that property, let us take a scalar lambda and find lambda x norm. Now by definition, lambda x norm means the supremum of mod of lambda xn. Now this can further be written as lambda mod into supremum of mod of xn, where supremum is taken over all n. Now by definition, this is norm of x. So we get lambda x norm is equal to lambda mod into x norm. Now the last property, triangle inequality. So let us take x and y, two elements belonging to the sequence space L infinity. By definition, x is a bounded sequence of the form having the coordinates xn, and y is also a bounded sequence having the members yn. Now let us find x plus y norm. By definition of norm in sequence space, this is supremum of mod of xn plus yn. Now this is further less than or equal to supremum of xn mod plus supremum of yn mod. Now by definition, this is x norm, this is y norm. Still yet we have proved all the conditions of norm. So this proves that the function defined by the supremum of mod, that is a norm on the sequence space L infinity. So we have proved the sequence space L infinity is a normed linear space. Now it remains to prove that this sequence space is a complete space. Then it will become Banach space. So in order to prove that this sequence space is complete, let us take a Cauchy sequence xm in this space. Now by definition, xm is infinite sequence having the members x1m, x2m, x3m and so on. Here m varies from 1, 2, 3 and so on in this way. Now we prove that this Cauchy sequence is convergent in the same space. Now let us apply the definition of Cauchy sequence. By definition of Cauchy sequence, for epsilon greater than 0, there exists positive integer, say n naught, such that for all m and m dash greater than or equal to existing integer, the norm of xm and xm dash, their difference, that is less than epsilon. Now by definition of norm, this is supremum of mod of xnm minus xnm dash. This is less than epsilon for all m and m dash greater than or equal to existing integer. Now because this supremum is less than epsilon, so this means every quantity is less than epsilon for m and m dash greater than or equal to existing integer. And this proves that the sequence xnm is a Cauchy sequence in the field of scalars, and field of scalars that is complete. So this Cauchy sequence will be convergent for every fixed n. So we can say that the sequence is convergent. Let us take the limit of the sequence as xn. Thus we can define x by using these xn. So we have defined x as x1, x2, x3 and so on. These are the components of the sequence which is denoted by x. Now we will prove that this x is bounded sequence so that it belongs to the sequence space L infinity. And also we are to prove that the Cauchy sequence xm converges to x. So firstly let us prove the sequence xm converges to x. In order to prove this, let us keep m fixed and m dash approaching to infinity in the equation 1. From that equation, if we take m dash approaches to infinity, now this limit is xn, so we get mod of xnm minus xn is less than epsilon for all m greater than or equal to n naught. So this implies that the supremum of these quantities is also less than epsilon, and by definition this quantity is the norm of xm minus x. This is less than epsilon, so by definition of convergence of the sequence in a norm space, we can say that the sequence xm converges to x. Now our last step is to prove that this limit function belongs to the sequence space L infinity. So it remains to prove, we are to prove that x is bounded. Now to prove x is bounded, now x is having the coordinates denoted by xn. Now let us consider xn mod. Now adding and subtracting xnm inside this mod. Now because this belongs to the sequence space L infinity, so this is bounded sequence. So by definition of bounded, there exists a positive real number mn such that the mod of xnm is less than or equal to mn. Now also for the epsilon greater than 0, there exists positive integer n naught such that xnm minus xn mod is less than epsilon. This is from the equation number 3 where we have taken m dash approaches to infinity. Now let us consider xn mod. adding and subtracting x and m and using the triangle inequality of real numbers here. So by using the triangle inequality, this is less than or equal to mod of this term plus mod of this term. Now from here, this is less than epsilon, and because this is from this equation, this is less than or equal to mn. So we have obtained, this is finite number, so we get the sequence x is bounded. So we can say that x belongs to M. M means the sequence space L infinity. So we have proved that the sequence space L infinity is complete. So this is complete normed linear space. So we can say that the sequence space L infinity, that is a Banach space. So these were some examples of the spaces which are complete normed linear spaces.